Good afternoon, all of you. In the previous class, we studied about Gibbs energy and how Gibbs energy is related to spontaneity. And in today's class, we are moving on to our next topic, which is entropy and second law of thermodynamics. Initially, we have studied about first law of thermodynamics and we studied about its applications and all. So now moving on to the next law, which is the second law. So we have few statements for second law of thermodynamics. So I have given three of them here. The first one is which is given in your textbook, which is for an isolated system, the change in energy remains constant and therefore increase in entropy in such systems is natural direction of a spontaneous change. This statement tells us that for an isolated system where we don't have exchange of energy or matter in that, so in that case the energy change remains a constant. So the energy change happening in an isolated system will be constant and therefore the entropy or disorder of that system is in the same direction of the spontaneous change or natural change. So this is a bit confusing statement of second law. So we have another statement where it tells that there is natural tendency of any isolated system to degenerate into more disordered state. So this sounds convincing. It tells us that the natural tendency of any isolated system is to get more disorder, or disorder is the most occurring or happy state of universe. If you consider isolated or non-isolated systems also in the universe, you can see the disorder will be increasing if it is a natural process. So if we consider a classroom, what happens in a classroom if teacher is not present? People will be randomly moving or they will be speaking with each other, making noise. Finally, we can tell entropy is increasing or randomness or disorder is the final result. So until and unless there is a control over any system, it will be in disordered state. So that's what the second law told. Not only the class, if we consider ice melting, what is happening? Disorder is increasing. The molecules are becoming more free from a solid state to a liquid state. The disorder is increasing. Or evaporation of water, that is also a spontaneous process. There also the entropy or disorder is increasing. If we keep our water coming from the hills, there also disorder is increasing. So almost any process which are naturally occurring, if you see, most of them are increasing their entropy or disorder is getting increased. That's what the second law told us. So the total entropy of an isolated system can never decrease over time. So if it is an isolated system, then the total entropy can never decrease. So until and unless we don't act a force upon it, entropy will not decrease. Naturally, any system will give us disorder or entropy increase. So the second law of thermodynamics explains why spontaneous exothermic reactions are so common. So when we told about spontaneous reactions, we told most of the spontaneous reactions are exothermic. It is giving out energy or giving out heat energy. So what is the reason for this? So according to second law of thermodynamics, in an exothermic reaction, the heat released increases the disorder of the surrounding and the overall entropy change is positive. So when we considered entropy, we were not considering that of just the system. We were considering is of the system and the surrounding. So entropy of the exothermic reaction, when we consider, the heat is getting released outside. So heat is going outside. So the entropy of the outside part or the surrounding is increasing. Then finally the overall entropy is positive. So that's why we get most of the systems as exothermic. So in an exothermic reaction, when the energy is given out, the given out energy is getting absorbed by the surrounding. So when the surrounding entropy increases, that also is counted in the total entropy. That's why in exothermic reactions, heat is released, increases the disorder and overall entropy increases. So hence reactions are spontaneous. So that is being explained by the second law. Now we are moving on to the third law of thermodynamics. But here we are telling about the entropy of molecules. We have seen a lot of molecular reactions, and molecules, whenever we say that they are not stationary, they are always moving. And this moving molecules will have different type of motion. Some are translational, some are rotational, some are vibrational, etc. So molecules will be moving always. It can be stretching vibrations, it can be other vibrations, bending. So a lot of type of motions are involved in molecules. And all these motions are some kind of work only. So work needs energy. That is also an obvious fact. So when you see these molecules, if we supply some amount of heat to any of this motion, what happens to it? So heat increases the energy, energy will increases more of motion. So as we supply heat, they will move more faster, and movement means entropy or disorder. So for example, if we consider this box, if we are giving more of energy to it, they will move randomly, and if it is a rotatory motion, it will move in a more faster direction or faster way. So that's why we can tell when we provide more heat energy, entropy will increase. So similarly, if you decrease the heat energy provided, the entropy will decrease also. So that's what the third law is stating. So when temperature of a system rises, these motions becomes more vigorous and entropy increases. All these motions will be more vigorous or very fast or random. That's why increases the entropy. And when the temperature is lowered, the entropy decreases. So the third law states that the entropy of any pure crystalline substance approaches zero as the temperature approaches absolute zero, or 0 Kelvin or 0 degree Celsius. This is called the third law of thermodynamics. So when the temperature given is 0, then all this entropy will stop, all this motion will stop, because there is no energy for this work. So hence what happens? They will stop moving. So entropy becomes 0. That's what the third law states us. The entropy or the disorder of any pure crystalline substance approaches 0 as the temperature reaches 0. So this statement is confined to pure crystalline substance because practical evidences shows that the entropy of solutions and supercooled liquids is not 0 at 0 Kelvin. So we are telling about pure crystalline solid. So pure crystalline solid means they already have a proper arrangement, or they are already having less entropy because they are very tightly packed in crystalline solid. But in case of supercooled solutions or liquid state of substances, if we consider, even if we reduce the temperature to 0, there will be entropy present. So that's why the statement is confined to be pure crystalline substance. There already the entropy is very less and they are very strongly bonded. In that case, if we reduce the temperature also, there will be zero entropy shown, because already some amount of entropy was there and we are reducing the temperature also. Hence it will become zero. But in case of supercooled liquids and all, they are already having more entropy. They are not very tightly packed. Even if it is super cold, they are not very much tightly packed. So in that case, if we reduce the temperature also, some amount of entropy will be present. The importance of the third law lies in the calculation of absolute values of entropy of pure substances from the thermal data. For a pure substance, this can be done by summing Q reversible by T from 0 Kelvin to 298 Kelvin. So the importance of third law is this, because with this equation, which is Q reversible by T, we can actually find out the absolute entropy values from just the thermal data. So the thermal data is dependent on the entropy. So if you consider the 0 Kelvin, what is Q reversible by T, and then we go to 1 Kelvin, 2 Kelvin. So if we consider from 298 to 0 Kelvin, we can actually get a rough idea or a good idea about the value or absolute value of entropy of that particular substance. That is the importance of this law. So with this, just with this equation and with the varying temperatures, we can find out the absolute values of entropy, as this is the equation of entropy. So now we will see a relation between spontaneity and Gibbs energy. So yesterday we told the Gibbs energy change is the factor which connects the enthalpy and entropy. And yesterday we studied about the factors which affect the spontaneity also, which are energy should be negative, or the enthalpy, change in enthalpy should be negative, and entropy should be positive for a good spontaneous reaction. And we didn't mention much about the temperature. So now when we compare the conditions, we will understand how delta H and delta S are related to spontaneity and how this factor or this T factor is important there. So we will start evaluating. So these are the conditions which is given in your textbook. So we will compare each of the conditions with the feasible conditions of spontaneity, so that the energy should be negative and entropy should be positive, and finally we will get the delta G as a negative value. So for us getting the delta G negative value, the energy should be a negative value and this one should be a positive value. So then only we will get delta G as a negative value, and we will compare each conditions. So the first condition, delta H or energy is negative, that is feasible, and delta S, the entropy, should be positive, that is also a feasible condition. So as both of them are feasible, we don't have any question there. The delta G will get a negative value, hence reaction will be spontaneous at all temperatures. Temperature is not a factor there, because when delta H is negative and delta S is positive, we will get the delta G value as a negative. So hence all the reactions will be spontaneous at this condition. Next condition we are considering, so delta H or the energy is negative, that is a feasible condition. Next, the delta S should be positive. So should be positive, but it is a negative, so it is not a feasible condition. Now comes the factor which is T. So when one of the conditions are not satisfying, then we should consider the T factor, because here when one of them is negative and the other is negative, so when delta S, this factor becomes negative, then this negative and this negative will become a positive value. So when this part becomes a positive value, we don't get the delta G as a negative value. So delta S is negative now. So delta S is negative, negative and negative became positive. So this term is bigger now. So the only way we get a spontaneous reaction is that the value of temperature will very much reduce. So at very low temperatures, this value becomes again a lesser one. So when T delta S becomes a lesser one, again we have a chance of getting negative delta G. So at only low temperatures, this will become a spontaneous reaction. So when the entropy becomes a negative value, we will go for the T factor, and when the T factor is very low, we will get the whole term as a smaller value, and finally we will get delta G as negative. So at this condition where the energy and entropy are negative, then we should get a low temperature for spontaneous reaction. And if we have high temperature in the same condition, then the reaction will be non-spontaneous. Only if the reaction is in low temperature, the T factor will reduce and this whole term will reduce and we will get a spontaneous reaction. And if at all it is a high temperature, we will get it as a non-spontaneous reaction. So next condition we will see, where we have both of them are positive. Energy is also positive, But actually energy should be negative for a spontaneous process, but we are getting is as a positive value, so hence it is not a feasible condition. In this place if you see, this is feasible because entropy is a positive value, that is a feasible condition. So here also we know should depend on the T factor. So when all the conditions are proper, we don't need to see whether the temperature is fine or not. Until and unless one of them is not a feasible factor, then we should see for the T factor or the temperature factor. And here we have the energy factor to be positive. So when energy is positive, again this sum will not give us a negative value. So there what happens is, this t value should be a very higher one. Then the whole term will become higher to cover up this positive value. For example, here if I am getting positive 5, so here I should get a bigger negative value or negative 6 or negative 8, then only the whole term will become a negative value. So that's why if this value is positive, then T should be a very high value. Then we will get a spontaneous reaction. So here both of them are positive, and at low temperature, if T is low, then we don't get it as a spontaneous reaction, we will get a non-spontaneous reaction. But when higher temperature is there, with the same condition, if we depend on T, at higher temperature we get reaction as spontaneous. And in the last condition, energy is positive and entropy is negative. So just opposite of the spontaneity condition. Energy is supposed to be negative and entropy is supposed to be positive. But in the last condition, we have both the factors to be in the wrong direction. So hence, whatever we do, whatever changes we do with the temperature, we don't get it as a spontaneous reaction. So this is the comparison what we have. So initially we had both the conditions to be feasible for a spontaneous reaction. If this is the case, then we don't consider the temperature also. We can directly tell that the reaction will be spontaneous at all the temperatures. And then we came through four conditions where we have one of the term is in the proper direction and the other was in the negative direction. So one of the terms in energy or entropy, if that is feasible, then we can adjust it with the temperature and finally we get a spontaneous reaction. But finally we have both the terms to be in the negative direction. So both energy and entropy, if they are showing the negative deviation from spontaneity, if we change the temperature also, we can't find a spontaneous reaction. We will end up with a non-spontaneous one. So this is the comparison what we have. Both the terms are feasible, we get spontaneous. One of the condition is possible, then we can try it with the temperature. Both the conditions are wrong, then no way. Finally, we will get a non-spontaneous only. So this is the comparison which is given in your textbook. So make notes on it properly and submit it. So with this, we wind up our session. Thank you.